Hello! Today we'll look at how we are speeding up PyTorch using Torchy, a tracing JIT compiler. Eager mode frameworks, such as PyTorch, offer a programming model which is way more convenient than previous generation frameworks, such as TensorFlow 1. You can just write a few operations and then print the result, which is very convenient for debugging. But eager mode frameworks are slow. Let's see how our example gets executed. When Python gets the first operation, PyTorch dispatches the multiplication to the GPU, which computes the result straight away. Then the result is passed back to Python. Again, the addition is dispatched to the GPU, which computes the result, and then we are back to Python. And again, we go to the GPU and back. To print a tensor, we have to transfer the data from the GPU to the CPU, so it can be converted to a string. As you can see, this execution model is quite inefficient. To make things a bit more efficient, frameworks have a bunch of hacks. For example, transpose doesn't really transpose, it just creates a view. So in this example, changing y also changes x and vice versa. One of the reasons to not materialize transposes is that they fuse very well with matrix multiplication, as matmul algorithms usually need to transpose one of the inputs anyway. Another hack is the creation of fused operations that combine multiple smaller operations in order to reduce all the dispatch overhead that we saw in the previous slide. But this places an extra burden on users to remember all the thousands of operations. Let's now do a deep dive on how PyTorch works. We start with tensors. There's a PyTorch tensor that lives in the PyBind world, which interacts with a PyTorch tensor in C++. A tensor holds a reference-counted tensor implementation, which then holds a storage implementation. Tensor and tensor implementations are just a view. They state how the data should be interpreted. For example, what's the data type, what are the tensor dimensions, and so on. Storage is the raw data and can be shared across multiple tensors. This decoupling of tensor-tensor implementation allows for multiple tensor implementations like dense, parse, and so on. Let me give you a few examples of tensor creation to make things clearer. Here, when we create tensors from data, we need to create new tensors, tensor implementation, storage implementation. When you do an operation, again, we need to create a new tensor implementation, storage implementation. When you do in-place operation, there's nothing new. We just override the storage. To is an interesting operation, so it only copies the data if the data types don't match. But if they match, it just bumps the reference counter. For transpose, as we saw before, it's just a view. So we share the storage and we just create a new tensor and tensor implementation. Now let's see what happens when you call a PyTorch function. PyTorch uses a dispatching mechanism to get to the right device. You can think of C++ vtables, for example. The dispatcher takes the hop and input data types into account to decide where to dispatch the operation. It also has a global state that takes part in the decision, but we'll ignore it for now. The dispatcher works in a waterfall way. The first handler to match wins. This handler can either compute the answer or do something and redispatch to the next handler. Bmap and batched are used for data parallelism. Autocast converts some operations from FP32 into FP16, similar to Apex. Then we have the tracer, which is used by TorchScript, which we'll discuss later. Then gradient computation, and finally, we dispatch to a device for computation. It's a quite complex process, but it gives us a lot of flexibility. What's available today to improve performance of PyTorch on a single device is TorchScript and the Microsoft Onyx ORT model, which uses TorchScript underneath and thus shares the same limitations I shall see in a second. I've mentioned there's also Autocast or Apex. TorchScript supports two modes. Let's start with tracing. The idea is that you provide a set of representative inputs, so TorchScript can execute the function with those inputs and record all the operations that were executed. It then produces an equivalent function in an SSA-based IR. The problem with tracing is that the inputs you give for tracing must go through the exact same branches as any subsequent call. For example, this code from the RADM optimizer has 4 possible traces depending on the input values. TorchScript only records a single trace corresponding to the path taken by the representative input that you chose initially. If a later input would go through a different path, you get the wrong result, as TorchScript cannot even warn you in this situation. So this form of tracing is quite dangerous, as you can get the wrong result without even noticing. TorchScript also supports compiling Python directly to the same SSA-based IR. However, the set of Python features it supports is very limited, and this is by design. If it supported everything, TorchScript would be just yet another Python compiler, not a tensor compiler. A lot of real-world code bases are just too Pythonic for TorchScript. It will never work for them unless people redesign their whole code to fit the TorchScript paradigm, which is not ideal. So, are we doomed? Is PyTorch inherently inefficient? And of course not. I wouldn't be here talking to you today otherwise. There's this famous quote in computer science that all problems can be solved with another level of indirection, except performance. But today, I'll show you that even performance sometimes can be solved with indirection. And this is Torchy, our new tracing JIT compiler. A fundamental observation that makes Torchy possible is that most tensors are not observed. Mathematically speaking, the program on the screen is a function from 2 tensors, x and y, to another tensor. The intermediate values of w are not observed. In fact, tensors can only be observed in very few cases, like for branching or printing. Say, when you print the loss, for example. Otherwise, most of the time we are just accumulating operations over temporaries. And this is the key observation. So the idea is to delay execution until observation. Instead of computing operations straight away, we accumulate them in a trace. Then when we get to an observation event, we stop and send the whole trace to the GPU for computation. Therefore, we save the whole back and forth to the device. Plus, we can optimize the trace, which is just a nice little program. Tracing JITs are not new. They've been a tremendous success for JavaScript. Because of the delayed execution, we can batch operations. We can also detect which variables are just temporaries and never observed, which is good for optimization. Traces can be optimized, and this cost is amortized as traces are executed millions of times. And best of all, tracing JITs work with any codebase and modified. No code changes needed. Torchy works by intercepting calls in a transparent way using the PyTorch dispatcher that we have seen before. The program needs just a single line to enable Torchy, which essentially changes the global dispatcher state to always dispatch to Torchy. We insert Torchy in the middle of the waterfall. Instead of executing operation, Torchy writes them in a trace and returns a dummy tensor. Later on, Torchy executes the whole trace either using the waterfall mechanism or by using alternative backends. These smallish straight-line programs are the dream of any compiler. PyTorch also has some observation events that don't go through the dispatcher. We have our own tensor implementation to intercept these events. For example, when printing, we may need to force the trace to be executed. We are in early days, so we have been running just a few benchmarks from Torch Vision and Hugging Face. For the sake of curiosity, just wanted to show you how BERT looks like from the perspective of Torchy. Circles are traces and arrows are jumps between the traces. We see that the whole BERT model consists in just a few traces that fit on this slide. Zooming in, I've copy-pasted the model diagram from the paper for reference so we don't get lost. Now we see the individual operation in each of the traces. Surprisingly, each trace corresponds roughly to a building block of BERT. We have the embedding layer, attention head, normalization, and feed-forward. Operations correspond one-to-one to the internal PyTorch operation, also known as A10. And here's the continuation of the model with more normalization, feed-forward, attention, and then the output. Today I've presented Torchy, a new tracing JIT compiler for PyTorch. It works by delaying execution of operations and batching them onto traces. Traces are then optimized and executed with the best backend. Best of all, Torchy requires zero code changes, even for dynamic models. Thank you for listening. I hope you'll be using Torchy very soon.